Okay, so we have now arrived at lecture 40, and this is the last ab initio quantum theory that we will discuss, which is the coupled cluster theory, which is currently known as the gold standard of electron correlation theories. After this, if we have time, next week Friday we will discuss DFT for one class, just like an introduction. But I believe you have an additional advanced quantum chemistry course which deals mainly with DFT, so uh, it is not mandatory. If we do not have time, we will not cover it. Okay, so far the last thing that you did was the many body perturbation theory, and that tells you how to add electron correlation as a perturbation on top of a zeroth order self-consistent field function, which is basically the Hartree-Fock function. So in coupled cluster theory, what we will do is we will also add correlation on top of the Hartree-Fock function, but it will be a non-perturbative theory. So it's the principle is a bit different. So we can start from what we know. So we have the Hartree-Fock function, and that we can write as a determinant of n spin orbitals, the n occupied spin orbitals, and the orbitals have been obtained from a Hartree-Fock procedure. So this is the Hartree-Fock determinant. And then from this determinant, we can generate some excited determinants or correlating determinants. We've also done this before for CI, and the notation is somewhat like this. Chi I to A is an excited determinant where I has been replaced by A. So you have A, J, blah, 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 N. This is an excited determinant. And because I have only replaced one orbital, it is called a singly excited determinant. So all this is familiar from CI, but I am using the new orbital labeling conventions that we discussed in my last class. So I hope you are comfortable with that. I'll repeat that after I finish writing the doubly excited. So doubly excited here, I and J are replaced by A and B. So this is a doubly excited determinant. What is the notation that I have used here? So I, J, K, etc. These are occupied spin orbital labels. So I'm using the letters IJKL for occupied spin orbital labels. I'm using A, B, C, D for virtual or unoccupied spin orbital labels. And when I use PQRS or something, then this is a general spin orbital label, which means that I'm not specifying whether it is occupied or unoccupied. So this is the current latest notation, which has now been accepted by the whole community, and everyone more or less follows this. Only old papers will follow different conventions. Okay. So let's see. So now if I wanted to write an excited determinant from the Hartree-Fock determinant, I can use the second quantized operators that we have discussed also. So in the Hartree-Fock determinant phi, I destroy an electron in orbital I and create an electron in orbital A. So that is basically generating my singly excited determinant chi I to A. Similarly, I destroy an electron in J, I destroy an electron in I, then I create an electron in B, and then I create an electron in A. So this will give me a sorry, I should write it the other way around because I want to keep the ordering of the orbitals the same. I destroy in I first, then I destroy in J, then I create in B, and then I create in A. So then I will get this one, A, B, I, J. Sorry, A, B, K, L, whatever. And now let's say I want to write a CI expansion with this notation. Then I can say that a CI function can be written as 1 plus C operator on phi. So my one part gives me back the Hartree-Fock determinant, and C contains one body operators, so which are of this type, and let's say two body and up to n body. So this will give you the with some coefficients. Okay, I guess you get the picture, so I'm not writing the full thing. So I can write my CI function, which is basically my correlated function, wave function according to configuration interaction theory, as a uh, as an operator acting on the Hartree-Fock function, where the operator has a linear structure. So 1 plus C may be called a linear ansatz. Now, what does this ansatz mean? The word ansatz basically means the guess of a form. So here you're guessing the form of the correlated wave function. And in case of CI, you're guessing that the correlated wave function is just a linear combination. So your ansatz is a linear ansatz. So it just has C. Now contrast with that, in couple cluster, you have an ansatz which is e to the power t. So that would be called a non-linear ansatz. Now I'll justify why it's like this, but just to tell you, and with different, even more complex theories, like if you have multi-reference couple cluster, that would also that can also have a range of Ansätze. Okay, so this is a German word, and it means the guess that you adopt for the form of the operator. Okay. So let's see now. Now, in terms of this C operator, let me try to show you why the CI fails on grounds of size consistency. So we've done this before, where you evaluated the uh, energy of two non-interacting hydrogen molecules and shown that it is not simply the sum of the energies of the hydrogen molecule at the CISD level. So if I only take C1 and C2, so singles and doubles, then the configuration interaction theory is not size consistent. You've seen this in the determinant picture. Now, if I were to write it as in terms of these C operators, how would I say it? So let's say two infinitely separated hydrogen atoms, hydrogen molecules, and that is a subsystem X and a subsystem Y. Okay. And I've taken a set of localized molecular orbitals for convenience. Then the then a coefficient which looks likeCijab, where I and J are on I and A are on fragment X, and J and B are on fragment Y, then this is 0 because they are non-interacting fragments. Okay. However, if I were to write the wave function, the psi Ci for this system, then you see that even though I can separate my total C operator into Cx plus Cy, because there are no cross coefficients and only those C coefficients exist where all the orbitals involved are on the same fragment. So C is equal to Cx plus Cy, but my psi Ci cannot be separated into psi Ci x into psi Ci y. So if this was a product separable function, then you could say that the two wave functions have become non-interactive. However, in case of Ci, because of the linear ansatz, you cannot separate the wave function, the total wave function, into the fragment wave function. So some spurious interactions remain, and that is also reflected in the fact that ECI is not equal to ECI x plus ECI y. So this is also not true as a result of the lack of product separability of the Ci wave function. So Ci wave function is not product separable. Okay. Therefore, Ci is not size consistent. Now, once I write it in this form, uh, it is possible to see that if my ansatz for psi was something like an exponential ansatz, if it was an exponential ansatz, then, and let's say my t has the same form as c, then when t is equal to tx plus ty, in case of a non-interacting system broken up into two x and y subsystems, then psi is equal to e to the power tx plus ty phi, which is equal to e to the power tx into e to the power ty phi. Okay. Of course, what you need is also the product separability of the underlying wave function, of the underlying reference function. So we will talk about that also. So this also needs to be product separable, which is actually true for the Hartree-Fock function. So I will go ahead and write that. So in CI, even if we went that far, so even if we wrote this as phi x into phi y, you see that you would still have cross terms. So you would have Cx phi y and Cy phi x terms. So even if we went one step ahead there, we would still not have the product separability of the Ci function. On the other hand here, I immediately get psi x into psi y. Or I had better write, okay, fine. This is not, okay.
Madam,
Yeah,
here do you assume the TX and TY commutes? Commute among
we
each other.
are assuming Tx and Ty commute, yes.
Okay.
And they actually do because all the cross terms are 0 in
Okay.
this when they are non-interacting.
Okay.
So this is only when we have this non-interacting limit. So we are using the concept of size consistency to justify what or guess what sort of answers would give you size consistency by construction. So this is sort of a good guess. Of course, the exponential ansatz was not developed from this consideration alone. So it involved a more elaborate and more prolonged sort of investigation into, because why would someone take an exponential ansatz suddenly? So taking a linear combination of the determinants is far more obvious than taking an exponential combination. But on hindsight, this is something that is the easiest to see. So I am starting with that. So in order to have a theory or ansatz that is size consistent by construction, the exponential form is one of the simplest forms for the ansatz. So that's why you take that one. Uh, Also, let's now talk a little bit about the underlying reference function. So you see that the product separability of the reference function is crucial to the size consistency of any correlation theory. Now, people often forget this. Okay. So, if you're doing a couple cluster theory for a system where your reference function itself is not suitable, then even though the couple cluster theory is sort of is a size consistent theory, and you know that, your results will not show size consistency. So let's look at an example. So if you do a Hartree-Fock theory for, so let's talk about the reference function. So I'm doing a calculation or a computation for the potential energy curve for dissociation of hydrogen fluoride. Okay, so this is hydrogen fluoride, not Hartree-Fock, and I'm doing the triplet pi state. Okay. And I have done a restricted open shell Hartree-Fock. Now, what does that mean? That means that all the orbitals which are doubly occupied in hydrogen fluoride, those have the same spatial paths accompanied by either an alpha or a beta spin to construct the spin orbitals, and the two singly occupied orbitals, those are uh, those are, let's say, both up. If it's so, I can choose them to be both alpha, and these two are also the same, also have the same spatial part because they are degenerate. Okay. So a restricted open shell Hartree-Fock calculation would give you an orbital set where the doubly occupied orbitals all have this, each have the same spatial paths pairwise, and the two degenerate singly occupied orbitals also have, well, they are of course in different directions. Won't say they're exactly the same, but they're symmetric. Okay, so you will have one pi orbital in the one p orbital or pi-like orbital in the x direction and one pi-like orbital in the y direction, and they would be degenerate in the triplet pi state. And I am following the potential energy curve to a dissociation to the doublet S state of hydrogen and the doublet P state of fluorine. Okay. I'm also doing, of course, restricted open shell Hartree-Fock calculations on the fragments. Now, since these are all the high spin ground states of the various components. So this triplet pi is a high spin state, ROHF, so doublet S is also high spin and doublet P is also high spin. Then ROHF can do accurate calculations, or I mean correct calculations on all the fragments. In which case, ROHF is size consistent in this case. Okay, so ROHF is adequate to describe both the supermolecule and the fragments, since they are all high spin. Now when I contrast it with another dissociation channel, you will see that where the problem lies. But if suppose I was studying the dissociation of the ground state of hydrogen fluoride, which is 1 sigma plus, and this also dissociates to the same fragments, then so these are the same fragments, but note that these are coupled to triplet while this is coupled to singlet, because it's arising from a singlet state. In that case, what you need ROHF to do over here is to describe an open shell singlet state, and that it cannot do with a single determinant. So with a single determinant, you can do a triplet, you can do a doublet, or you can do two doublets coupled to a triplet. That you can do. So the supermolecule computation here is still a triplet in the first case. So RHF can handle it. However, if you want them to be coupled to a singlet, two doublets coupled to a singlet, you need two determinants, minimum two determinants. So to describe the supermolecule in singlet state, you need doublets coupled to singlet. This can be done only with a minimum of two determinants. And as you know, the Hartree-Fock picture is a single determinant picture, so it cannot do this. Therefore, ROHF cannot do this with a single determinant. So if you're doing this second dissociation channel of the singlet HF, then your the Hartree-Fock itself will not be size consistent, and this would translate to a lack of size consistency even at the couple cluster level. Okay, so you have to be always careful of this. Okay, and if you remember another discussion, I think last class, where I spoke about size consistency versus size extensivity. I'll talk about that again now. So size extensivity basically means the scaling of correlation energy with system size. So if this follows a consistent pattern for any system sizes, for all system sizes, then the theory is said to be size extensive. And coupled cluster is also size extensive. Okay. And that continues to hold. So the size extensivity of the theory is never broken, although the size consistency may be broken. And this is sort of a statement in the air for you now, because it is, and I don't think I will go into that in this course. It's a little beyond the scope of the course. But for those who are interested, I can tell you there's something called a linked cluster theorem, which tells you how the algebraic structure or the operator structure of a theory in second quantization is related to its size extensivity. So if you can show that what they say is that all the terms in the equations are connected, then the theory is size extensive. So there is a theorem like this, and since this is unrelated to the underlying reference function or anything else, it only depends on the terms in your working equation for the theory. Size extensivity is a relatively more independent quantity. Okay. This is just to give you a perspective. This is not something I expect you to realize now. But just be aware that size consistency and size extensivity, these are distinct. They are like two different concepts. They are related but distinct. And why I mention this is because especially older literature use these two terms interchangeably. So you may get confused. But just try to see what context they're speaking about it in. Most often people will be talking about size consistency. Okay, size extensivity sort of more or less more crops up if when you're contrasting CI and coupled cluster, or if you're dealing with something that's entirely in coupled cluster theory. So then you will see size extensivity becomes a more common thing to talk about. Anyway, this is just a side note in a way. And the next thing that I will tell you is now what the ingredients of the coupled cluster theory are. So let's go to the coupled cluster formalism. So like I said, the T operators are basically just like the C operators. And you also break them up into single excitations or double excitations. And the terminology that you use is one body, two body. Okay. So a one body T operator is basically an excitation operator accompanied by a coefficient. And the coefficients, the TIA, these are called cluster amplitudes. So this is called a one body cluster operator. And these are called cluster amplitudes. And this is the operator, the actual operator which generates the excited determinant, and that can be written in shorthand as EI to A operator. So every cluster operator has an amplitude part and a operator part. Similarly, I can write T2, and T2 is IJAB, TIJAB, AA dagger, AB dagger, JAI. Okay. And the 1/4 comes from the fact that this is an unrestricted summation, but you only have as many cluster operators as there are unique pairs of IJAB. And if I want to write an n-body cluster operator, then my accompanying factor is 1 by n factorial squared and sum over ij blah 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 ab blah blah blah, however many you have. So this is a general one. Okay. And depending on up to which rank T operator you take, you get your various approximations of coupled cluster theory, like coupled cluster singles doubles, or coupled cluster singles doubles triples, or singles doubles quadruples. Okay, whatever. Now, if on the but now see how it is different from CI. So my psi is e to the power t phi. So if I approximate t to be t1 plus t2, which is the most common approximation, you get coupled cluster singles doubles, CCSD. Then I can write psi as e to the power t1 plus t2 phi. And you have many terms. So you have 1 plus t1. So let's do the linear term first. 1 plus t1 plus t2. So that looks just like the CI. But after that, you have all the non-linear terms. You have 1 by 2 factorial t1 squared. You have 1 by 3 factorial t1 cube plus 1 by 2 factorial t2 squared. Okay, no, this was not systematic. Let me write it more systematically. So let's do the square terms first. T2 squared plus, so you have a T1 half T1 T2 plus half T2 T1. So I can add them up to one term. And then I do the cubes. 1 by 3 factorial t1 cube plus 1 by 3 factorial t2 cube plus 1 by 2 factorial t2 t1 squared plus you can have actually more terms, and at the fourth power I can have t1. So basically you have lots and lots of terms over here, but we'll see how this also gets reduced by the structure of the working equation. So e to the power t1 plus t2, this is basically an infinite series, right? But it will naturally stop at a point when you have exhausted the number of electrons. So you're exciting uh, electrons in your Hartree-Fock determinant to virtual orbitals. So when you have excited all of them, then you can have no more T operator. So let's say if this was a 4-electron system. So if it was a 4-electron system, then so 1 T2 is fine. T1 square is a double excitation, fine. T2 square is a 4-electron, fine. This is 3 electron, this is 3 electron, this is now T2 cube. T2 cube is a 6-electron excitation, so that would not work. Let me write this in red so that so if this was a 4-electron system, then the T2 cube term would not be there. T2 T1 square is also fine. T1 to the power 4 is also fine. Okay. But a lot of these terms would then not be possible, and you would end up with a finite number of terms. So I think I've covered almost all. So with 4F2, you would get this, and this. Okay. But you don't need to evaluate so many terms. We will see that when we do the working equation. Then so let's start doing the working equation then. So here we start with the Schrodinger equation. So let's see, let's do the working equations. So I have the Schrodinger equation, which is H psi equal to E psi, psi being the exact correlated wave function. We have guessed that the form of our correlating ansatz is e to the power t acting on the Hartree-Fock function. Okay. Then if I project with the Hartree-Fock function, so here e to the power t, only the 1. If you expand e to the power t, the first term is 1, so only that will survive, because with the other terms you generate excited determinants, and because of intermediate normalization, your overlap of phi with some chi, that will be 0, chi being an excited determinant. So you will only have phi left. So we have now got an expression for E. So let me mention that intermediate normalization is assumed here, which means that the overlap of the Hartree-Fock function with the correlated psi CC function, that is 1, which means that any overlap with excited functions is 0. So we've already got the expression for the energy. Now what we now need to do is, of course, we need to know how to evaluate the value of this quantity, of this matrix element of h e to the power t. And the other thing that we need to know is to find out the values of the t variables. So we have these cluster amplitudes inside the t operator, so we need the values of those amplitudes. Now, if I were to write phi h e to the power t phi. So I'm not writing the hat all the time. I get a bit tired writing the hats. That is equal to phi h 1 plus t plus t squared by 2 factorial plus t cubed by 3 factorial, etc. Phi. So here I'm writing the full t. So this t contains t1 plus t2 plus t3 or whatever. Then I have phi h phi plus phi h t phi plus phi h t squared by 2 factorial phi plus phi h t cubed by 3 factorial phi, whatever. Okay. Now let's remember Slater's rules again. So H, I know, has two parts, a one body part and a two body part, and my T's will excite to excited determinants. So this part will give me some sort of an excited determinant. And if this excited determinant differs by more than 2 orbitals from phi, then by Slater's rules, my matrix element will be 0. Okay? So, okay, so the first one can definitely survive. The second one can survive. Okay. So let's look at the lowest rank operator actually. Let's look at just T1. So that will give me the limiting case. So even if I only have T1, then my second term is fine. It differs from chi differs from phi by only 1 orbital. In the third term, chi differs from phi by 2 orbitals. That is also fine. But from the fourth term onwards, see, even if the T is just a one body operator, the chi that I generate from here will differ from phi by at least 3 orbitals. So H being up only a two body operator or having up to two body operator, this matrix element will be 0 by Slater's rules. So there is a natural truncation of this series due to Slater's rules. Truncates this. So at least my energy is a reasonably closed expressions. It's not a series. So it has one term which is just phi h phi. Then you have a ht phi, and you have a phi ht squared by 2 factorial phi. So I have three terms in my energy expression. Now, of course, depending on what operators you choose in your T, meaning how whether you do a couple cluster singles, doubles, or singles, doubles, triples, etc. Different rank T operators will contribute to different terms. So in the linear one, you can have up to two rank 2 operators. In the non-linear one, you can only have a T1 square, as you can see. Even if you have a T1, T2 over here, this will become a triply excited determinant on the ket. So the matrix element will be 0. So in the energy expression, you only can only have T1 and T2. So this is an interesting thing. So even if I do a couple cluster singles, doubles, triples, quadruples, whatever I want, pentuples, my energy expression will still contain only singles and doubles. But what will be different? Since you have taken the 3, 4, and 5 body operators, the they will contribute to the values of the 1 and 2 body cluster amplitudes. Okay, so this is only the energy expression. We are still to determine the equation which will tell us what the Ti to A, Tij these cluster amplitudes, what their values should be, and these values will of course change if you take, or improve even if you take triples, quadruples, etc. But in the energy expression itself, you will only have T1 and T2. So do we have enough time? Okay, so we don't have enough time actually. Okay, I'll go ahead and write it. So before we can evaluate the amplitude equations, or the equations which will tell me the values of the cluster amplitudes, I will have to tell you about an operator identity which is called the Baker Campbell Hausdorff expansion. So this is an algebraic identity which tells you that if you have an operator string which looks like e to the power minus t h e to the power t, so here I've used t and h because that's what we will use for couple cluster. You could have written it as minus a b e to the power a if you like, okay? Because this is simply an algebraic identity. It has nothing to do with the Hamiltonian or the cluster operators. So the algebraic identity is H plus HT commutator plus half HT commutator, commutator with T again. You can put a factorial here. have, so it's basically lots and lots of nested commutators, and it follows a pattern, so it's easy to remember. You get the patterns. So basically, if you, this is called similarity transform. So if you have a similarity transform of an operator with another operator, you get, you can simplify that to a series of nested commutators. So I am writing this without proof here. If you are interested, you can look up the proof. It's an algebraic proof, so it's nothing very difficult. So we will use this in order to determine the working equations. Okay. Now, how will we do that? So we have h e to the power t acting on phi gives me e to the power t acting on phi. So this is what we had from the Schrodinger equation. And now I multiply with e to the power minus t from left. For operators, it is important to always mention whether you're doing it from the left or the right. So e to the power t phi. E is a number, does not matter. So this becomes 1. And now I left project with an excited determinant. Now this can be a singly excited determinant or a doubly. So if I do it with a singly excited, then I get chi I to a phi e chi I to a phi. Now remember that we have that by intermediate normalization, this overlap is 0. So this is basically 0. Similarly, if you do a left projection with the doubly excited determinant, you get chi ij ab minus dh phi equal to 0. Therefore, the working equations for couple cluster amplitudes, so that is the set of Ti to A, Ti to J to AB, etc. All the unknowns that I need to determine. The working equations have the generic form this. So it's a simple thing. So you have the Hamiltonian transformed by e to the power minus t and e to the power t. And on the right hand side you have 0. So this is quite a simple form for the equation. If you go into the details, of course, with this given truncation of t and therefore a given set of excited determinants, then you will get the explicit expression. So we'll do a few of the explicit expressions next class. So today we'll stop here. It's 4 o'clock. And I will, okay, I'll stop sharing and also go through the last parts, last few lectures, and come back with your questions because we only have next week before your exams. Okay.
And ma'am, is there going to be any other class test?
No more class test or assignments.
Okay.
You'll have directly the end sem sometime in May. whenever the schedule comes out.
Okay, so as of now, we can you assume that Viva is not going, or what will we assume?
No, I'm not discounting it yet. Just hold on. Let me talk to Professor Pal again.
Okay.
And but the Viva, it will not be something that you'll have to study for. So it will be okay.
Yeah. I mean,
Yeah. We can also do it after the NSEM, I think, before the date. If your exam is not very not right at the end at some time, let's see the schedule. And the vivas, we can do it according to your convenience also. Any like 1 or 2 persons at a time, no problem. Let's see. I'm not discounting it yet. Okay. So bye for today.